In this final section of the course, before we wrap up, I'm going to talk a little bit about what's really driving the interest in hydrogen across so many industry sectors. And I'm going to approach it based on my background as an engineer and entrepreneur with data and economics. There's lots of ways to look at it, of course, but that's what I'm going to present in this set of slides. So the first question, obviously, that should be asked is why transition away from fossil fuels? Well, on the left-hand side is some of the greenhouse gas issues that we are living through very much so right now. You've seen that list before, I'm sure. Everything from more violent weather patterns, rising sea levels, reduced ice extent in glaciers and in the South Pole and Antarctica and so forth, and the North Pole. But there's also a whole series of things that come along with fossil fuels, if you look at the lower left, that we've accepted over more than 100 years as part of the price to pay for the energy needs that are provided by fossil fuels. And these are related to public health and represent extremely large casualty losses, both property and human, and income potential for families and so forth. So that's been around for a long, long time. We know about greenhouse gases much more recently, within the last few decades. I'm going to deep dive a little bit more into this topic, but I just wanted to give you some links in your PDF slides. The Climate Time Machine that is provided by NASA online. You can see some of the latest data there. I also would like to point you to a very interesting congressional hearing, testimony and talk by the late Carl Sagan 40 years ago, believe it or not, where he predicted very accurately, if you listen to it's not too long, listen to his testimony, exactly what we're living through right now, and it was based on his knowledge of planetary science. So let's dig a little bit deeper into this. So the next question then is, why transition to hydrogen, given what I showed on the previous slide? Well, to mitigate everything on that previous slide, the use of hydrogen eliminates all of those negative impacts. Now you've got to look at the whole life cycle. As I mentioned, it's the use of hydrogen where you don't have any other greenhouse gases, no particulates, no smokes, and so forth. How you make the hydrogen, of course, is very important in terms of the life cycle to ensure that it has those benefits throughout its life cycle. But one of the interesting things about hydrogen is it's an energy carrier, a storage method, and a fuel. It can be all three of those things simultaneously, or depending on the function, any one. And as the middle paragraph shows, I mentioned some of these already: no carbon emissions, no harmful environmental impacts. A few other things that make it intriguing as one of the solutions in our portfolio to tackle this problem is there's no strategic materials or supply chain issues. These are very common materials that are used in liquid hydrogen systems. No disposal or recycling challenges. System lifetimes measured in decades. These liquid hydrogen systems, as I talked about in the first history of hydrogen lecture, have been around for 60 years plus and are still in operation with routine maintenance and no significant replacement costs. The other thing that doesn't get talked a lot about is that you produce prodigious amounts of potable water, that is drinking water or drinkable water, when you use hydrogen, particularly in a fuel cell. It's very easy to collect that water and use it for a variety of sources or reasons. Agriculture, drinking, humidity control, depending on your system. So very important, very unique aspect of hydrogen to keep in mind as you develop systems. So here's some of the data. This is land and ocean temperatures for the year 2023. You can see much higher. Record warmest is the dark red, much warmer than average is the sort of pink, dark pink color, and so forth. Most of the globe, of course, has been in the much warmer to record warm region in the year 2023, which was the last data available as I was recording this. This is plotted a little different way and looking at it historically. Those same land and ocean temperature, and this is now anomalies, It's pretty easy to see the pattern there, consistently going higher and higher, warmer and warmer in terms of the land. This is land and ocean temperatures. And you can also see the trend. You'll see more of this as we go on. As fossil fuels have increased in usage and our energy demands have increased, so have these temperatures. But we'll talk about that in future slides. Again, this is just pure data. This is nothing more than data of temperatures that we measure by satellite and buoys in the ocean and other means. Daily global sea temperatures. This is there's a mean line in there. The dashed middle one is the mean, and then it's 2 sigma above and below that, or the other dashed lines above and below that one. You can see that in the year 2023 and then halfway through 2024, how far above 2 sigma, if you know your statistics, we are from the mean in terms of global sea surface temperatures. So again, this is just purely data, looking at data here. This is where we're getting now into more looking at the qualitative impacts now. Although qualitative is a term that maybe we should use carefully here, because there are very severe economic impacts to all of what you see on this slide. And I won't go through all of it, but these are just anomalies and events in 2023 reported by NOAA. We're going to keep seeing this over and over again, of course, in years to come. And again, these are all economic impacts in terms of losses, property losses, measured in many, many billions of dollars, and lost income for people who are injured or killed and their family who live through these anomalies. So let's dig a little bit more into the greenhouse gas topic. These are the list of the top 4 greenhouse gases on the far left column, and then in the next column over shows you the atmospheric concentration of just these greenhouse gases in the atmosphere. So that adds up to, the total 100%. So it's a pie chart basically of the greenhouse gases that are shown there. The next 2 columns are the ones that are of most interest, or very interesting at least, and the next one over is the atmospheric lifetime. So carbon dioxide, of course, is what is getting and has been getting most of the attention. 76% of the greenhouse gases are carbon dioxide. It remains in the atmosphere for thousands of years. So we're talking about generations here, and the impact of that is in generations. So that cost that we talked about, economic costs, we talked about in the previous slide, is not just now, it's generations, millennia into the future for the greenhouse gases that we're producing now and what we have produced in the past. This is unlike any other business model, if you think about it that way, where a great deal of the costs are borne not just by the users or by those who are profiting from the business, but by the entire global community, and in fact all of the life on the planet for thousands of years going forward. Something to really think about and consider. So the last column is the global warming potential over a 100-year period, and it's normalized to carbon dioxide. So carbon dioxide is 1, so keep that in mind. So the next line down, methane, which is the primary constituent in natural gas, is now getting a lot more of attention, even though it's a smaller concentration of the greenhouse gases, 16% roughly, and has a much shorter atmospheric lifetime, which is good, 10 years. But look at the global warming potential, 25 times higher than carbon dioxide. And I'll show in some slides, there's been a gross underreporting of the leaks, natural gas leaks and methane leaks throughout the globe that are now being measured by satellite that shows just how critical this situation is in terms of greenhouse gases and methane. The other 2, nitrous oxides produced in any combustion process, it has to do with dissociation of the air at the high temperatures of combustion. It's somewhere in the middle between the 2 in terms of lifetime, but a very, very high global warming potential, something that needs to be looked at. And of course, if you're going to fuel cells, which hydrogen supports, you eliminate that nitrous oxide. And even if you combust the hydrogen, there's a lot of ways to reduce and minimize the amount of NOx that's produced. The last one is a little bit, even though it's a little scary to look at some of those numbers, fluorinated gases. It's a little bit of a success story, and I think a promising anecdote or example of when the global community comes together and begins to ban certain substances that are affecting the atmosphere. Fluorinated gases, if you aren't old enough to remember, we're eating away the ozone layer, and we're finding huge gaps in the ozone layer, which protects the Earth, of course, from rays from the sun, damaging rays. Ultraviolet, I believe, is what the ozones were blocking out. I'm sorry, yeah, the ozone was blocking out. The community came together globally and got rid of refrigerants that had fluorinated gases and many other sources, including aerosol cans, hairspray, and so forth. And there's been a recovery, a dramatic recovery in that ozone layer. So I think it's a bit of a success story, something we can look towards perhaps as a template for how we tackle, although it's a much larger problem, of course, with a lot more vested interest, the production of greenhouse gases. So a little more data on the left-hand side from before 1960s all the way up through today. Pretty clear and consistent trend of the increase in carbon dioxide in parts per million in the atmosphere. Again, this is strictly data. On the right-hand side, though, is going back based on ice core data, so all the way back to 800,000 years in the past, forward to now. Humans came on to the planet around 300,000 years ago. So the highest before in the history of our species was about 300 parts per million based on ice core samples, and we're now up around 420 parts per million. So you can see the dramatic, our species has never existed in the carbon dioxide parts per million concentration that we currently have in the atmosphere, and of course it's growing, as you'll see in the next few slides. Here's a comparison of the amount of carbon dioxide that was annually produced in emissions. That's the gray line, and then the atmospheric carbon dioxide parts per million measurements over that time frame. So again, very clearly you can see how they track together, and unfortunately the trend of where they're going. Now, if all of that is starting to get you a little depressed, first of all, you're taking this course, so hopefully you're getting the tools to help us solve this problem. But here's some scenarios. So in the scenarios, the dark red line, of course on the left-hand side is historical. So that's up until now. It's already happened. So on the left-hand side is the plot of the production of carbon dioxide and emissions, and then on the right is the parts per million carbon dioxide that is in the atmosphere. So this is the same data we just saw previously, and now we're taking the historical data and looking forward into projections. So the dark red line is if we continue on a very high rate of emissions, and you can see where the parts per million go. Remember, again, it was something around 300 parts per million was the highest ever in the going back to the prehistoric history that we had in 800,000 years ago. Over that range in the atmosphere, and we're getting well beyond that if we continue to emit at those high rates. Now, the good news is if we reduce that down, and these are all plausible scenarios that have been put out by NOAA's reports, we can get down into that light blue line, and you can see there's a bit of a lag, but over a period of a few decades, we actually start to drop the parts per million of carbon dioxide. So this is the promising message. And the key reason why hydrogen is an important part of that portfolio of solutions that we need to use and make use of to tackle this problem. Now I mentioned methane. This is, you can see the link down below. You can read more details about it. It's from satellite data from a European Space Agency satellite. Showing methane emission sources. And again, as I mentioned, if you read the article, you get more details about it. Many of these, both the sources and the magnitude of these leaks, were grossly underreported in previous years. Not a surprise, because many of these are industrial leaks that don't really, the folks making them don't want to report them. But it's a much more serious problem than was previously thought. And on the left-hand side, if you look at the legend, you can see that these are from urban landfills, or the kind of the orangish color, and then red is gas, blue oil, and green coal. So you can actually see what the source of those methane, and again, methane being the primary constituent of natural gas. So what those sources are and how large they are on the right-hand side gives you a sense of how many tons per hour is being emitted from those sources. So atmospheric methane, may not surprise you, has been following a very similar trend, and these are from leaks again. So going back through about 1980s, early 1980s, up and through today, you're seeing the increase in atmospheric methane. This is an important, and again, a link below to this report, an important thing to keep in mind. This is deaths and greenhouse gas emissions from energy source. Again, as I mentioned in that very initial slide, it isn't just the greenhouse gas emissions, which are very important and very serious. It's also what are the deaths and injuries? What is the cost of these various fuel types that are well known, have been well known for a very long time, that we're living with? And if you go down the list, of course, coal, oil are the ones that have the greatest impact on both of those areas. And then it gets lower with natural gas, but again, as we just went over, the greenhouse gas emissions, a very serious problem with the infrastructure leakages. Biomass, and then of course, as you get into the renewable energy sources, you reduce on both sides of that graph. So that's the incentive to go to these renewable sources, which of course can be stored as hydrogen and used later. Now, if you, just to make sure that we cover this, one way, of course, to reduce emissions is to reduce our energy demand, and we saw some of that during the pandemic. We were forced to see some of it because of the measures, the health safety measures that had to be taken to reduce the spread of the pandemic coronavirus. And we saw a drop in the emissions, and a corresponding drop, was due to less energy usage, less transportation, less travel, and so forth. But that was very short-lived, and we're back on path of growth. And you can see in each of these areas, industrial, transportation, residential, commercial, even with the variability in the projections, they're all growing. So we're not going to get out of this problem by reducing our energy consumption, at least not realistically. I mean, we certainly should try, and that's part of the puzzle, but it's not going to get us there. So our journey together, and again, congratulations to you for taking this course and for building the tools to begin to address this, is going from the left-hand side of this slide to the right-hand side in the use of hydrogen, where we eliminate a lot of these, all of these problems potentially if we go all the way to hydrogen. In all of the industry sectors that are shown there. And by the way, hydrogen is being used in all these sectors, some in demonstration mode still, some fully operational, and moving very quickly in that direction. This last slide I'll show is from the Department of Energy, and it's their concept of an overall hydrogen at scale integrated energy system. Now this is for the US, but it would apply to any region and globally as well. Hydrogen on the right-hand side as a feedstock or a fuel to multiple uses, industry sectors, and applications. Many of these it's already done and has been doing for a long time, but some of them are newer. And then, of course, you got the production of hydrogen in the middle, which can be from water, from waste, biomass waste, and many other feedstocks, which produce that hydrogen. And then, of course, above that is the power generation. As we bring more renewables online, intermittent renewables, we can use that stored hydrogen to follow our demand, our energy demand, with use of fuel cells or generating hydrogen generation turbines that will keep our demand following grid going even with high renewables, intermittent renewables as our sources. And then on the left-hand side, some of the ways that the energy can be obtained in a way that is attacks, again, some of these issues we already talked about, greenhouse gas emissions as well as pollution and other emissions. With renewables, potentially nuclear, and continued potential use of fossil fuels if we can do carbon capture, utilization, and storage. And a lot of that is still in demonstration phase. So I'll end with that, but there's our hopeful look at what the transition to hydrogen can look like. As with all the other sections in this course, there are supplemental slides in your PDF downloadable slide package. So you can look through those and get some more data and more in-depth data. And of course, on the left-hand side is the QR code for this course.